Welcome back, everybody, to lesson two. And we're going to take a little different approach. In lesson one, I wanted to really give you topics that you would have some familiarity with. And since most of you are engineers in one way or another, mechanical, industrial, environmental, mechanical properties of materials were something that you could definitely get your hands around and see. Now, in this lesson, I want to go back and sort of start a little more at the where traditionally these types of courses will begin, speaking of materials. And what it really comes down to is crystalline structures. And so what we're talking about here is how atoms arrange themselves to create these materials that we're used to seeing. In the original, the lesson zero, we might have called it, or the introduction, we saw how the periodic table became involved in how we dealt with materials. Now we're going to delve a little deeper. And what I do want to say is we're not physicists, so we're going to look at things in maybe a little more of a practical way, where atomic structures are important to us, but we're more interested in how those atomic structures give us some of the properties that we're going to look at. And so, speaking of physicists, take a couple quotes from a rather famous physicist, or infamous in some people's minds, Edward Teller. He was heavily involved in the Manhattan Project and throughout the Cold War and strategic defense initiatives. And he had a couple really interesting quotes, I thought, is the science of today is the technology of tomorrow. And that's for sort of materials people, and I like the idea of thinking myself more as a materials engineer than anything else. We rely on a lot of fundamental understanding of how, say, in some cases, atoms or different components of materials at different size scales interact with each other. And these really lay down the groundwork for what we consider the technology that you're going to apply. And so this is really the course comes down to that fundamentals. And then, as always, nice little quote about physicists, where physics is simple, but physicists, having worked at a physics lab, physicists in a lot of cases definitely are not as simple as some of the physics. So in this lecture, what we're going to talk about is really atomic structure. I'm going to give you a background on what the atomic structure and what is important as we move forward. But the really important thing is crystal structure and how these crystal structures define different metallic systems. And when we start thinking of a unit cell, that is our way of defining long-range order. Because when we talk about crystallinity, we're going to see that there's a difference between what we may consider short-range order and long-range order. And metals very much are based on a long-range order, and they're based on three basic crystal structures that we'll look at. There are a series of other ones, and I'll show you the images of those and how complex they can get. But we're going to be fortunate when we talk about metallic crystal structures that these ones, in the scheme of things, are rather simple. And we'll talk a lot about that. And then how we can use these crystal structures to calculate the density of materials and really get that theoretical density. So we're going to move back in Callister. The idea right now is to go to chapter 3. And with that, we have a certain number. As always, I recommend that you do the practice problems, but as well, the ones with the asterisks are the assigned problems. So please do those and turn them in at the assigned time given on Canvas. And so a little more important terminology here. We start to expand a little bit out of what we saw with really stress-strain behavior and mechanical behavior of materials. We start getting into some things that may bring back some other memories for you. Is atomic number, mass, weight, atomic mass unit, sort of these ideas of how an atom operates. And then the bonding between atoms. And this is where we really start to get a little more interested as material scientists. Is not so much of what's going on within the individual atoms. We leave that to the realm of the physicists. But we're interested in bonding and then how these different individual atoms bond together to create these unit cells with that long-range order. And within these unit cells, we have body-centered cubic, face-centered cubic, and hexagonally close packed. And they may at first seem to be rather complex names to you, but really remember with materials scientists and materials engineers is really are masters of the obvious. So we give a name of body-centered cubic. It actually almost fully describes the crystal structure. It's a cube. There's an atom in the center. Face-centered cubic. Once again, it's a cube. with atoms centered on each face, so face-centered cubic. And you can imagine hexagonally close packed is in the shape of a hexagon. So from an obvious standpoint, these are good things to remember, is that don't always get caught up in a long name, but the names typically mean something. And so keep that in mind as we move forward. So I'm not going to really revisit too much of what you've taken in physics up till now. You've taken atomic structure, you've taken some quantum mechanics in all likelihood. So you have some idea of the atomic building blocks and how we look at it. And so I didn't want to spend a lot of time on atomic structure. And so this is, in some cases, some people consider it a silly little video. But everything you need to know, and that I believe you need to know, at least for this class on atomic structure, is included in this nice little video. So enjoy.
Simple science. What is an atom? Chemical elements such as hydrogen, helium, carbon, and oxygen are made up of tiny particles called atoms. Atoms are extremely small, but they are made up of even smaller particles called protons, neutrons, and electrons. Protons and neutrons are about the same size and weight as each other, while electrons are much smaller and lighter. Protons have a positive charge, electrons a negative charge, and neutrons have no charge. Protons and neutrons join together to form the nucleus at the center of an atom, while electrons circle around the outside. An atom always has the same number of protons as electrons, and usually the same number of neutrons. For example, helium has 2 protons, 2 neutrons, and 2 electrons. Carbon has 6 protons, 6 neutrons, and 6 electrons. Hydrogen only has 1 proton and 1 electron, and no neutron. Each time you add an extra proton to an atom, you get a new chemical element. But if you only add another neutron, you just get a heavier version of the same element, called an isotope. Protons and neutrons are made up of even smaller particles, called quarks. Inside each proton or neutron, there are 3 quarks, held together by other particles called gluons. Electrons are very small and light and can easily be stripped off the outside of atoms to provide electric power. One thing these electrons can be used for is to help scientists examine atoms up close. By firing high-energy electrons at an atom and watching how they bounce off the atom and how the atom changes when it is hit, scientists can learn about the inside of atoms.
So for this class, that is really a pretty good primer. It goes over all the components of the atom, but when we start thinking in terms of structural materials, and when we think of structural materials, I think one of the important things to really take into account is the scale of what we're thinking of these materials. We're not really as interested in a lot of cases in what's happening at an atomistic level. We don't want to go to large particle accelerators and start breaking apart different types, different atoms and looking at neutrons. What we're interested in is building larger structures. But there are certain building blocks to these larger structures and for these materials. And it comes down to these atoms. And what we're interested in really is materials, and primarily structural materials, is how do these atoms arrange themselves? Now, I will say it now, and I'll say it a couple more times as we work through the lecture, is really physicists hate the way we look at atoms. What we're going to look at atoms in this case are as hard spheres and how they arrange themselves. Now, physicists will look at that and say there's an electron cloud, there's this, there's that's going on. You have all of these particles that are rotating around these orbits at high speeds. And that's all well and good when you're looking at the subatomic level, but we were trying to simplify that subatomic level to allow us to understand how things occur over a much larger scale. And so we're going to look at these atomic arrangements and these interactions. And so we look at these atoms as the primary building blocks. We know they contain this. We know the mass of protons. And I put these here because if you look at it, these are small, 10 to the negative 27th kilograms. From a mass standpoint, they make almost no mass. But what we're going to find is that there's a couple things that we're really interested in as materials people when it comes to these atomics. You're going to hear me throughout the course use the terminology, and a lot of materials people use it without really explaining it very much to other engineers, but we really like to talk about Z numbers. And Z numbers are strictly that atomic number, so the number of protons in the atomic nucleus. Not always worried so much about atomic mass, but we do worry about isotopes. And as in the video said, you add a number of neutrons, you maintain those protons, but you take away or add neutrons, you can create isotopes, where you have two materials that are basically the same element, but they have different atomic masses. And so we're going to look at that here in a second, but remember Avogadro's number. There's a certain number of atoms in 1 mole of material, and 6.023 times 10 to the 23rd atoms, a number to remember. And so let's go back to where we always start, and whether it's in your high school physics class or in some other ones that you might have, always start with carbon, because we know carbon can exist in all these different forms. Graphite is one of them, a pencil. And so we see graphite. Graphite's also extremely unique in its thermal conductivity. And as I say this, if you go on to the YouTube machine or some other videos online, there are places where you can see where people can take graphite and cut an ice cube in two without melting it. And part of that is because graphite has extremely high thermal conductivity, and we take advantage of that. But we take those same carbon atoms, we rearrange them, we create the hardest of materials in diamond, or even amorphous carbon. Used to be the coatings, scratch-resistant coatings for eyeglasses used to be amorphous carbon, but we see amorphous carbon used in all kinds of different applications where we want to have something that's a little more scratch-resistant or where we want to apply a hard coating. Now, fullerenes are buckyballs. If we get even more complex in the arrangement of our carbon atoms, these buckyballs or these fullerenes, they have some unique properties, but they really came about. They were discovered in the late 80s, early 90s, and it earned a scientist at Rice University the Nobel Prize one year for his discovery of these. And they were discovered almost completely by accident. One of his graduate students was really they were interested in some carbon experiments, and they were taking a high temperature plasma torch and basically spinning a graphite bar very quickly. And I think they were more interested in making looking at certain plasma interactions. But what they did was when they started examining the soot that came off of that, what they discovered was these very complex crystal structures. And it came out to be these buckyballs. Now, there was a lot of interest for a number of years. There's still interest here or there, but one of those things where it can take on this shape, but we really haven't quite figured out what to do with it yet. Another one, and sort of one of my favorite examples, is uranium. We know how important it is in the nuclear power industry and going back to the Manhattan Project. But really one of the first commercial uses of uranium, and strictly of uranium-235, and this is the radioactive version of uranium, or the enriched uranium. It's only about 0.72% of the natural uranium, so it takes a lot of effort to extract it from its other isotope, which is uranium-238, which is depleted. It can be used in a number of different types of applications that we see, and one of my favorites is counterweight. It's a replacement for lead. We know lead's toxic. Depleted uranium if it has any, has a very small amount of resident radiation out of it. And counterweights. Cranes was one of the more unique application spaces that I've seen for this. But uranium-235, uranium-238, same element, extremely different uses. And Pennsylvania was fortunate that the Shippingport Atomic Power Station was really the first commercial nuclear power plant in the U.S., and it was in Beaver County, Pennsylvania. And what we see here is the original reactor. There's a photograph of the original reactor, And it was originally designed to go onto a submarine, but it was placed here, and this atomic power station was used within the Pittsburgh region for decades. It's since been decommissioned, but it was really the first commercial use here in Pennsylvania of enriched uranium. But we see like the range of different uses just by changing a couple neutrons or taking away or adding a couple neutrons to the material.